Okay. Hi, let's wait a minute while we wait for other people to join. And I get the a little organized here. Okay. Um, so usually it takes a few minutes for people to join in. So while there's no viewers, I'll just answer some of the questions that have been submitted, and then put them on or send out the link to the YouTube video. Okay. So let me first answer this question by Rui, who says, Dr. Kaffa, could you explain the asymptotic briefly on the asymptotic test or asymptotic distribution? Here's a question. Let me just write out what he says here. Here's x1 to xn are IID, and f of x equals x cubed e to the negative x over theta divided by 6 theta. You have to check and make sure that that's a proper density. Okay, and then, okay, so that's the start of the question, and then it continues on. It continues on and says asymptotic distribution is n goes to infinity. What is a power family? So this is a fairly complicated question for both these classes, but let me describe it in generality as if people might find it useful. So, so first of all, the MLE, both classes that this office hour is servicing discuss the MLE. So the MLE, just to remind us, stands for maximum likelihood estimator. Okay, and if we have probably the most common circumstance is if, you know, like here we have this data, and let me refine this notation. Let's say this is the density, and let's just put here, just to remind ourselves, that it depends on this parameter theta. Okay, the idea of the MLE is that let's say, because these observations are independent and identically distributed, we take the product, I equal 1 to n, of the density, f of x, evaluated at the data points, right? And multiply all those together, and that creates an object that is called the likelihood, okay? And now the distinction between the collection of densities and the likelihood is that the likelihood views the parameter. The parameter there. Oh, I need my pen back. Views the parameter as the function argument, and the density views the data, the x value, as the function argument. So take as an example, let's take it as an example, our f of x, let's say our x's are binary, and that f of x is p, or let's use theta because we're using theta already, theta to the x, 1 minus theta to the 1 minus x, right? Then, my f of x, there we go, f of x, comma theta, okay? Then where each one of my x's is a yes or no. Then when I construct my likelihood now of theta depends on x is now theta. We take the product, I equal 1 to n, theta to the xi, 1 minus theta to the 1 minus xi, and that now equals theta to the summation xi, 1 minus theta to the n minus summation xi. Okay, and this likelihood then describes, according to the model, this likelihood describes, according to the model, the various support for the different values of theta. So here, if we were to plot the likelihood, we would have now theta on the axis, and we would have L of theta on the vertical axis, and higher values would represent better supported values of theta given the data. And then, in fact, the point where this reaches its maximum, right, is obviously special, and it is the point such that the it's the best supported point in the data given the model. The other interpretation of the MLE is that it is the point, the value of the parameter, that makes the data that we observed most probable, right? So we don't know theta, but if we had to pick a theta, why don't we pick the one that makes the collection of x's we observed most probable? Okay, and that point is called the maximum likelihood estimate. Okay, and if you were, in this case, to maximize the log likelihood with respect to theta, you end up getting that the MLE is theta hat, which is summation xi divided by n. Okay, so that's a lot of background on the MLE. So the sample proportion, and that's why we like the MLE. Is in many cases it gives us kind of the estimators we know to be correct. And so because it gives us those estimators that we know to be correct in the cases when we would like, then it's then we have some trust on this for the cases where we don't know, and that's so that if you for example plug in the MLE into or if you run a generalized linear model, the estimates it's giving you are MLEs, where it's less clear in those more complicated settings what is exactly the right answer. In this simple setting, we know that if the answer wasn't p hat, there would be a problem with the MLE. It wouldn't be the problem with p hat as an estimator. Okay, so at any rate, the broader point is that MLE is not an asymptotic technique. The MLE is a technique that gives you an estimator. It's a finite sample technique, right? We didn't need any asymptotics to say that this is the MLE. This exists as a good estimator without any regard to asymptotics. Now, where the asymptotics come in is if we want to perform an inference about theta, in that we want to perform an inference to say something like h naught theta equals 0.5 versus HA theta different from 0.5. Now, in this case, we know some things about the MLE without actually using any asymptotics. We know that in this particular case that it's unbiased, that expected value of theta hat is theta, and we know its variance. Variance of theta hat is theta times 1 minus theta over n. So we know some finite sample properties of the MLE in this specific case. However, its distribution, even in this simple case, is a little bit hard to work with, and so we rely on asymptotics. And I think what Rui is asking is, it seems like the MLE for a lot of circumstances, has asymptotic normal behavior, and we tend to kind of form the same kind of confidence intervals. And so that's that question is true. It's a very well understood question in the for people who study statistics, and it's basically the idea that we know that under a pretty broad set of circumstances that MLEs, maximum likelihood estimators, have asymptotic normal distributions, and we happen to know the kind of specific form of the standard error of the MLEs, the asymptotic standard error of the MLEs, and so that's where those things come from. That's why it always seems to pop up. And just in case you're wondering, how do they get that? That seems almost impossible that someone would, that they would derive that that the maximum likelihood estimate is asymptotically normal. In fact, because the only real tool that we have for establishing, asymptotic normality is the central limit theorem. Maybe a couple other small things, but the central limit theorem is sort of the big hammer. Well, here we'll give you some insight about how it becomes true. If you look at the likelihood, it's really, if you look at the log likelihood, it's really the sum of the log of the densities evaluated at the data points, right, as a function of theta. Okay, so if I were to multiply that guy by 1 over n, which doesn't change much, if you look at it, this is actually an average, right? So it has asymptotic normal behavior. So anyway, that's how they prove that. So the long answer, the short answer to Rui's question is that there are results that suggest that maximum likelihood estimates are asymptotically normal. There are results that those results also give us the asymptotic standard error for the maximum likelihood estimate. On top of those facts, there is some set of results that say that the maximum likelihood estimates are optimal. They have sort of minimum variance. And so there's a lot of asymptotic results associated with MLEs. They're beyond the scope of this class, but like if you're wondering where they come about, they really kind of rely on things like the central limit theorem, and they're not that tricky to establish once you learn the one or two tricks that are used. But that's where that's coming from. I think your intuition of hey, I'm seeing a lot of, every time I calculate an MLE, there's some sort of related asymptotic trick that we're deriving in an ad hoc manner for every special case. Is there any sort of unified reason to why this is all working out? And the answer is yes, that is exactly true, and it boils down to the theory of maximum likelihood estimation. However, that theory is just complicated enough to where we wouldn't want to cover it in this class. But if you wanted a good reference on it, you could look at one of my favorite books. Look at something like Casella and Berger, which is a mathematical statistics textbook, and in that book it'll cover some of the basics of asymptotics of maximum likelihood estimates. And then if you really want a detailed treatment, then you would have to look in some of the more advanced asymptotics books. But if you look in any kind of serious book on asymptotics, it will cover it. I don't know if it's in Layman's book, but I really do like Layman's asymptotics. It's pitched at the right level. If you really want to dig into the math quite a bit, then his book is pitched at the right level. The most of the books are at a much higher level than that. Okay, so that answers that question, I believe. Okay, let's see. So Tahir has a kind of a long question. So let me take his afterwards, and I'll look at this question from Dung Tran here, and let me select it. Hello, Professor. I'm having a question regarding one or two-sided test. Please correct me if I'm wrong. One-sided test is used if we want to see one mean is greater than the other, while two-sided test is used if we want to know if the means are different. That sentence ends, but because there's a character limit, but I'm presuming the end of that phrase would be if there's any difference whatsoever. So that's correct. So let me just write, let's do the difference in two means because it's at least a little bit more interesting than a difference in one mean. So you have the mean for, let's say, a treated condition minus the mean for a control equal to 0 versus HA, the mean for a treated condition different from the control is greater than 0. Okay, so this is the example of the one-sided test. And of course, this is equivalent to H naught mu T equal to mu C versus HA mu T greater than mu C. Of course, that's the same. Okay, so you're testing this. You are you are really banking on on being quite sure that the only direction you're interested in proving that the treatment and control are different, the only direction that's worth looking is in the direction that the treatment is specifically greater than the control. So you know, in this case, you might be thinking something like, with the treatment, whatever you're studying, it can't possibly do harm, right? And so you're not interested in looking at the treatment. Like if it's a diet pill, let's say there was some quiz questions on a diet pill. If it was a diet pill, that there's no way this treatment could cause you to gain weight, so then you would only look in that direction. So it's testing a different hypothesis. However, Dung's question is a little bit more complicated than the math. The math is quite easy. The math says look at a one-sided test if you're interested in a one-sided hypothesis. If you're only interested in the treatment being larger than the control or not, then look at a one-sided hypothesis, or less than the control or not. Then look at the one-sided hypothesis. And if you're interested in it being different whatsoever, then look at the two-sided hypothesis. The math is pretty easy on that. However, I would also add that there are kind of odd cultural conventions that have, not odd, but cultural conventions that have come about in testing in quite a few scientific literatures and regulatory agencies and places like that, where they have kind of procedures, even if there's no way that mu T could be less than mu C. There's places, outlets such as certain scientific venues that demand that you do two-sided test regardless. And that, of course, is the simple way to think about that is that's going to double all your p-values. So if you're, in a lot of the sort of regulatory agencies require in specific tests that they have to be two-sided, and there's an element of kind of conservatism to that, that sort of bias towards the null. So, at any rate, it's kind of a more elaborate question than the math. Right, the math is quite easy. If you are only interested in one side, then do a one-sided test, and if you're interested in two-sided, the two means being different, then do a two-sided test. However, I would say it's a little bit more nuanced than that because of the phenomenon of different sort of cultures of how people adopt the testing procedure for their particular area. So I'm quite confident that your question probably came about because in your area or wherever you're working, there's a cultural convention to always doing a two-sided test or something like that. So that why do we even bother to teach one-sided tests? And that's a fair point. But so I'm hoping that this discussion will clarify that for you. Let's see. Let's see. Okay, so let me. So Rui entered. Just to elaborate on this previous question, could you talk a little bit more about consistent, biased, and unbiased estimators? Okay, so an estimator is consistent. So let's say, just from before, theta hat is an estimator that is trying to estimate the population parameter theta, and let's say theta is the mean of the density or something like that. Okay. and let's just say this theta hat is based on IID data, and let's put a little n on it to allow ourselves to discuss what happens as n goes to infinity, right? So so if this is true for all n, right? If expected value of theta hat sub n is equal to theta, then we're going to say that theta hat, the estimator, is unbiased. It's not an asymptotic property, it's a property then, but if it's true for all n. If it's not true for all n, if maybe something like this is true, that this goes to 0 as n goes to infinity, then we might say something like theta hat sub n is asymptotically unbiased. Okay, so there's a difference between being unbiased and being asymptotically unbiased. If theta n converges to theta in the sense of the word probability, and so let's just remind ourselves. So we had a lecture at one point where we talk about consistency and convergence and probability. So as the most canonical example is if you flip a coin a lot and take the proportion of heads, that proportion converges to the success probability of the coin, the head probability of the coin. Okay, so if this statement is true, if as you collect enough data, the probability, and the exact statement is that the probability that theta n hat minus theta being bigger than epsilon goes to 0. If that's the case, then we say that theta hat n is consistent, and what that basically means is that if we collect enough data, theta hat sub n becomes what it's trying to estimate. As you collect enough data, theta hat sub n becomes what it's trying to estimate. If we flip the coin enough times, that proportion of heads sort of turns into the true proportion of heads. Okay, so that's what consistency is. So we've covered biasness, asymptotic unbiasedness, biasness and unbiasedness, asymptotic biasness and unbiasedness, and then so things like power families and things like that. That's a little bit technical for this. Well, all this question is kind of a bit technical for these classes. But you know, there's so let me just a parameterized family is any density that you know depends on a parameter. So our binomial example is, you know, we were talking about earlier, theta to the x, 1 minus theta to the n minus x, or 1 minus x, right? That is a parameterized family. If you did 0.5 to the x, 1 minus 0.5 to the 1 minus x, right? That is a non-parameterized family. That's just a specific instance of a Bernoulli with theta equal to 0.5, but there's no parameters. There's nothing left to estimate. A parameterized family is a family where there's an unknown parameter, and basically all interesting, you know, all interesting densities have a parameter or something in there, so that and that's the kind of part of that's the process of modeling, right? So you assume something about the density, you know, in terms of its shape and its form, but you leave some things left out, and then you're going to use your data to inform that part that you've left out. That's the process of statistical modeling. So as an example, if you assume that your data is normally distributed, right, you usually assume it's normally distributed, but you say it's normally distributed, but I don't know the mean mu, and I don't know the variance sigma squared. Okay, so you've created a parameterized family, the Gaussian, that depends on two parameters, the mean and the variance, and you're going to use your data to inform those unknown parts of the density, the mean and the variance. Okay, and so you've modeled out most of the distribution. You know, by assuming it's Gaussian, you assume it looks, you know, that the population looks, you know, something like that, right? That the Gaussian says something about how likely people are to be so many standard deviations out into the tail, and at what rate that decays. It, you know, sort of decays at e to the minus x squared, which are a lot, you know, all a collection of assumptions. So you've taken the family, the Gaussian density, you've left two parameters unknown, and so that's what we call parameterized family. The power family distribution is just one of many families of distributions that, what statisticians do, whether, when they talk about exponential families or power families or whatever, they try and create, either highly restricted or highly general and flexible collections of densities that have certain properties. So the normal distribution has a bunch of nice properties, so it's a nice kind of little family of densities to consider when you index it by the mean and the variance. But in some cases, it's too restrictive to think in terms of just the normal distribution. So you might want to consider a broader family, of which even the normal distribution with an unspecified mean and variance is a special case. And there's so-called a collection of densities called exponential families that I find quite useful. And so, at any rate, the power family, you can look this up. All these families of distributions are just much more general classes of densities that some people find useful. It's part of our kind of math upbringing for most statisticians that they like things to be as abstract and general as possible, so they try and come up with collections of densities that contain lots of other interesting densities. Okay, so let me just finish this thought on Dung's question. So in a one-sided test, could I set the parameter, lower dot tail equals true? Okay, so let's just be specific about this, because this is kind of a highly little R associated question. So Dung had earlier asked about hypothesis testing and one-sided versus two-sided test. So when we manually do our hypothesis test, and let's just assume it's a normal test or a t-statistic, okay, and for a mean, with the important caveat, I can't stress this enough, if you're testing the difference between two means, keep track of which one was subtracted first and which one was first and which one was subtracted. In other words, make sure you remember whether you did A minus B versus B minus A, because everything totally changes, reverses itself in a one-sided test. But let's talk about the test of a single mean. Okay, if you want to test H naught mu equal to mu naught versus HA mu less than mu naught. Okay, that's one example of a one-sided test. The other example in this setting would be HA mu greater than mu naught. Okay, so this, what I'm drawing right here, this is the distribution, this is the density of the test statistic, either asymptotic or its exact finite sample density or whatever we're modeling as the density of the test statistic under H naught, okay, and the test statistic is consistent with the hypothesis in the sense that we're going to reject, in this case if the test statistic is too small, and we're going to reject in this case if the test statistic is too large. Okay, so let's consider this case right here, where we're interested in testing whether mu is less than the hypothesized value mu naught. Okay, so we're going to reject if our test statistic is too small, and we want to calibrate, right? We want to calibrate that probability with respect to having a very small chance of that happening if the null hypothesis were true. Well, this is the density under the null hypothesis right here. Okay, so if we were to say we'll only reject if our test statistic is smaller than that value right here, this quantile right here, okay, that would make that probability small. So we can set that quantile, say, for example, so that that probability is only 5%. And if your test statistic followed a standard normal distribution, you would do Q norm 0.05, right? And then lower dot tail equals true, and that would give you the correct quantile. However, just because by how the normal distribution works, you could also do Q norm 0.95, because I don't know, we always like to talk about the specific upper quantiles. Lower dot tail equals false, which is Oh yeah, no wait, lower dot tail equals false. Yeah, so lower dot tail equal true is the default. Lower dot tail equals false. Okay, in R. Okay, that would give us this quantile. And if we were testing this hypothesis, that would be the wrong quantile. However, you can just take the negative of it and it'll flip it over to there and it'll give you that quantile. Okay, so you have to be careful when doing these calculations or when looking at the notes. Sometimes we can do tricks like that or specify things in that way. Um, um, Specify things in that way. Let's see. So I want Q norm. Here I want lower dot tail equals true. Now I think about it because I want it to be 0.95. Lower dot tail equals true, and that would give you the part that has area 0.95 underneath it, but you would still want to take the negative of it. Okay. So at any rate, that is that is if you're manually doing the test. Now, if you want to do something like t.tests, one of the most useful functions in R, it does all of this for you, right? To do this test, right, you've got to create the test statistic, you've got to find the rejection region. And then let me also remind you here how you would calculate a p-value is you find whatever the value of your test statistic is, and you find the probability of being lower than it if you're testing this hypothesis. If you're testing this hypothesis, you would take your test statistic and find the probability of being higher than it. And if you're doing the two-sided one, you would take the smaller of those two and multiply it by 2. Okay? And there again, you have to be careful about how you do lower tail or upper tail. But a little bit of kind of error checking while you're doing this usually corrects these little those little mistakes. However, if you want to avoid them entirely, you can do the function t.test. And the function t.test, you put in your data as say x, and the mean that you're hypothesizing. But if you don't want to do that, you can actually subtract from your data the mu naught value. That'll do the same thing. And the arguments of t.test will tell you whether that it's the test of less than, whether it's greater than. If you give it 2 vectors, you can tell it whether it's a paired test or an unpaired test, and all these other things. So it'll keep track of these things for you. But anyway, I think that answers your question. But let's see. But put it in the comments if you want me to answer it some more. Could you please let's see. Okay, so let me see. Problem 8 on the quiz. Okay, let me look. All right. Okay. And then Tahira, I will get to your question. It's just you asked for several of them, so I figured I might as well do these little ones first before I do the big ones. Okay. Okay, let me read this question. And I will, I was kind of running out of time, but I will put some homework problems that will help people practice on these problems. So I have a homework set up for quiz 3. I'll put a homework set up for quiz 4. It just takes me a minute to write them. I usually do it late at night too. So just give me a couple days to get that out, and so I'll give you some practice problems on this, and you can try on the practice problems a bunch of times before you try on the real quiz attempts, and the practice problems are enough, should get you in the right mindset for the quiz. They kind of match up with the quiz questions. Okay. So let me talk about question 8. Researchers would like to conduct a study of 100 healthy adults, detect a mean brain volume loss of 0.01 millimeters cubed, assume that standard deviation. Okay, so let's see. So this is a power question. So they have n equal to 100, okay, and they want to, for every person, take their x follow-up, and they want to subtract, yeah, X follow-up minus X baseline, right? They want that to be, they want the this expected value. They want to be able to detect. Let's call that thing delta. They want to detect that delta to be. They want power to see if that delta is 0.01 or less. So because this this is lost, right? The follow-up brain volume will be less than the baseline brain volume. We would expect this number to be negative, so we're talking about a brain volume loss so that we want to be able to detect a delta of minus 0.01 or lower, and if you would subtract in the opposite order baseline minus follow-up, you would be detecting a delta of 0.01 or greater, right? We're assuming that the standard deviation is 0.04, okay? And then what would be the power for a study of 5% test versus no volume loss? So we want to test the null hypothesis that H naught delta equals 0 versus HA delta less than 0. Okay, so power, so in our test statistic in this case, and we're assuming what would be the power of the study of a 5% one-sided test? Okay, so the test statistic, let's say, is X bar minus the hypothesized value, mu, naught under the null hypothesis over sigma over square root n. Okay, and in this case, our mu naught is 0, so it's just that. So our test statistic is just that. Okay, so we want the probability. Okay, and when will we reject, right? So we're going to reject, right? Here's our distribution of our test statistic under the null hypothesis, which is a mean standard Gaussian, and we're going to reject if that test statistic, if we subtract it in this order, follow-up minus baseline, if we subtract it in that order, we would be rejecting if that guy is less than a standard normal z of 0.05, okay, which is equal to, by the way, the negative of a z of 0.95, okay, and then if we subtract it in the other direction, baseline minus follow-up, we would be rejecting if our test statistic was larger than z of 0.95, which is, by the way, equal to the negative of z of 0.05, because this density, if you rotate it around 0, is the same thing. Okay, so I like to subtract follow-up minus baseline, so I want to look in the negative direction. So we're gonna reject if our test statistic is less than z of 0.05, which is negative 1.645. Okay, and under the null hypothesis, under the null hypothesis that delta is 0. This has probability 5%, okay, because we calibrated it that way by choosing this quantile, right? We want the probability of rejecting to be small, okay. But under the alternative hypothesis, right? Under under the null alternative hypothesis, that is no longer 5%, okay. Right? And so, let's see, we want it, and the thing about power calculations, you always have to assume a specific value, right? So we said in the problem that we want it to be 0.01 or smaller, and one of the problems of this is that our test statistic under this guy is no longer standard normal, right? Because we didn't subtract off the correct mean. We subtract off 0, which is the true mean under the null, but is not the mean under the alternative. Now, one thing you can do is you can re-standardize this test statistic, and if you do that, that'll give you a formula. Okay, but you don't actually have to. We can calculate what's the distribution of our test statistic under under the alternative. Okay, so the expected value of our test statistic is equal to the expected value of x bar, right, over sigma over square root n, which is equal to delta over sigma over square root n, and the variance of our test statistic is equal to the variance of x bar over sigma squared over n, okay, which the variance of x bar is sigma squared over n, which works out to be 1. Okay, so under the alternative, our test statistic has mean this guy and has variance that guy. Okay, but this we can plug in, right? That's 0.01, our sigma is 0.04, and our n is 100. Okay, so now we have all the calculations. So all we want, so our test statistic is normal because, you know, our test statistic is normal because x bar is because we assume that our data was normal. Averages of normal data are again normal. Okay, so we know that our test statistic is normal whether it's the null or the alternative. And then we also know we know its mean, and we can plug into the mean, and we know its variance, and then we just want a Gaussian probability. We want the probability that normal with this mean and this variance is less than that quantity. So it's not so bad. And in the notes, I actually show how you can, you know, in the lectures I show how you can normalize your test statistics so it's back to being a standard normal, right? You just need to add and subtract the delta in the right way, but you don't have to do that. If you want, you can just calculate the the mean and the variance of that normal distribution and calculate it directly using the p-norm function. Okay, so try that, and I'll also give some practice problems. Yeah, and so yes, TS does mean the value of the test statistic. So when I write throughout when I've been writing TS, I meant test statistic. Okay, so now let's answer to here. I may not get to all of your question, but let me answer some of your question. Okay, so question 1. Okay, so the question says, in a random sample of 100 patients at a clinic, you'd like to test whether the mean RDI is X or more using a 5% type 1 error rate. The sample mean had the sample mean had X bar equal to 12 and a standard deviation sigma equal to 4, or S. Let's just leave it at sigma. What is the largest value? So we want H naught mu equal to X versus HA mu greater than X that you would reject for. Okay, so this is a kind of a boundary problem, right? So let's just remind ourselves how we would reject in this case if we had a specific value of X. Okay, so our test statistic in this case is going to be X bar minus the null value, which, you know, a little confusingly is X in this problem. Let me write it as mu naught. Okay. Okay. X bar minus mu naught over sigma over square root n, and we're going to assume this test statistic is standard normal. Okay. So here's the distribution of our test statistic under the null hypothesis. It's standard normal. It has mean 0, has variance 1, so that one standard deviation around the mean has about 68% of the density included in it. 2 standard deviations has about 95%, and 3 standard deviations has about 99%. Okay, so we want to reject under we want to find, let's see, so the quantile that we're interested in here is 1.645. That's our standard normal. And if we reject, because remember this is the distribution of our test statistic, we're going to reject if our test statistic is larger than that quantile. So let's just write that out. We're going to reject if x bar minus mu naught, which in the problem I'm calling x, over sigma over square root n is greater than the test statistic. And I see that there's a typo in the quiz that I'll correct. So if we want to find this boundary point, we change this inequality to an equality and solve, right? And you have pretty much everything that you need in the problem. You have x bar, which is a number that you plug in for. You have sigma. You have n, right? And we have this quantile that and I wrote a test statistic there. We're going to reject if that's bigger than this quantile. We have this quantile, so all that you're left with is this one point, and then you can solve for it. And I see that maybe what's confusing you is there's a typo. I'll correct the typo, which is weird because I thought I corrected that typo because it came up. But I'll double check that. I'll double check that. I thought I had corrected that, but maybe I didn't hit save when I corrected it. And then let's see. Which was the next one? Okay, so you asked about question 2. Question 2 is a standard 2-sample t-test. One thing to factor in is whether or not it's paired or independent group, which is the 2 main sort of t-tests that we'd figured out. So decide whether it's paired or independent group, pick the correct one, and then just try using t.test in R. Let's see, so 4. Okay, so 4 is a kind of a binomial test. So let me give you kind of a related test. Someone comes to you and says that that a coin is fair, and you want to ask how many, let's say a coin is fair. Let's take it as an example. You have a friend that had 5 kids, and all of them were girls, and you're questioning that gender for this person is a coin flip. You're saying there's something else going on. Okay, so here's the we want to test the hypothesis that probability is 0.5 versus where p is equal to probability that the child is a girl. And let's forget about twins and all these other intricacies of this problem versus HA, the probability that it's greater than 0.5, which is what you're thinking, right? And here you got, what is it? What did we say? 7 out of 8, or let's say, just to make up a number that's a little bit smaller. Let's say 4 out of 5 kids were girls for this person. Okay. Then this is a binomial, and we want to do the exact calculation. It says, so we want, we're obviously going to reject the hypothesis, the more girls that this person has, right? So we clearly wouldn't be surprised if this person had 2 or 3 girls. It's a little bit surprising if they have 4 girls, and if they have 5 girls, it would be very surprising. So we're going to reject, in this case, probability X is greater than the observed value, right? That would be the p-value, right? The probability. So we're going to reject for larger numbers of girls. So simply the number of girls that this person has is a test statistic. So if we wanted to calculate a p-value, it would be the probability of getting as many or more girls than we actually observed, right, under the null hypothesis, right? And the null hypothesis is that p equals 0.5. So this is a binomial calculation. So it's the probability of getting, so it's the probability that x equals 4 under h naught plus the probability that x equals 5 under h naught. And both of these are binomial probabilities, okay? And so because they're binomial probabilities, you can just plug them in. You can do p binom. There's several different ways to do it. Question 5. Let's see. What was the question 5 was the next one. Okay, so this is a Poisson, so think exactly along the lines of this kind of problem where, the count, it's exactly just the count that is of interest as a test statistic, and you want to calculate the exact Poisson probability under the null hypothesis. Okay. Let me see, 5, and then 11 was asked by 2 people, so let me do 11 as well. Okay. Okay, so this is a 2-group test. It's asking you to. This is a 2-group z-test. I think maybe some of the confusion here might be the common variance versus a non-common variance. But actually that should not make any. Yeah, it actually says that the standard deviation is 12 for both groups, so that's not. It shouldn't make a difference since the actual standard deviations are the same. At any rate, this is just a standard normal test. So I tell you what, since there's a lot of questions on quiz 4, why don't I'll try tonight or tomorrow as much as I can to get some practice problems for quiz 4 out there that are related. This will give you a chance to practice on some sample problems before you have to submit your official questions. So let me do that, and then after that, I think a lot of these questions will be answered. And I apologize, but I have to run off to a next meeting. So given, I think Tahir was the name of the last person, and Dung have some questions, and I think several other people have some questions on quiz 4. Let me take a stab at creating some practice problems, and then when you do them, I think you'll understand the quiz 4 questions a lot better. All right, thanks everyone for tuning in, and I'll be in touch as soon as I can with those practice problems.